This is the largest engineering project in the north of England, bringing thousands of jobs and significant challenges as construction continues around the clock.
Precision starts here. Diamond-tipped CNC bits carving through mass with high-pressure cooling jets. This is a billion-dollar ballet of cranes and modular engineering, moving in perfect synchronicity. Hidden inside is a duplex stainless steel skeleton, scanned by ultrasonic sensors for even the smallest imperfection. 25 tons of weight, hanging by a thread, balanced by real-time hydraulic adjustments. The physics of the central tower are extreme, distributing millions of tons of force into the deep bedrock. Every peak is reinforced with specialized alloys and ceramics to withstand the atmospheric friction. A 6-axis robotic arm achieves half-millimeter precision where traditional methods would fail. We use infrared 3D scanning to bridge the gap between ancient blueprints and digital reality. This is more than a building. It is a monumental legacy of high-tech engineering at the edge of possibility. Time-lapse simulations prove its stability. It is built to withstand tremors that would level a city. Computational fluid dynamics guide our design, letting air flow through to reduce catastrophic wind pressure. Stainless steel bolts integrated into granite, zero tolerance, absolute structural integrity. At night, it stands as a glowing beacon of human ingenuity, dwarfing everything around it. Welcome to the workshop. This is where the raw materials of the Earth become the icons of the future. Hydraulic force is our primary lever, exerting thousands of tons of pressure to seat these massive girders into their final position. Alignment is a game of millimeters. We use laser trackers to ensure every module is perfectly centered on the global coordinate system. Inside the structure, a web of high-tension cables provides the necessary pre-stress to counteract the immense weight of the crown. Orbital welding robots deliver a level of consistency that human hands simply cannot match, creating hermetic seals in seconds. The vertical shafts serve as the nervous system of the tower, housing high-speed logistics and technical umbilical cords. Thermal management is critical. Giant carbon fiber fans move thousands of cubic meters of air to prevent heat buildup in the core. We monitor the structure's thermal skin in real time, comparing live sensor data against our predictive digital twins. Navigating the canyon between these towers requires precision flight and specialized scaffolding that grows with the building. Every joint is treated with UV-sensitive resins, ensuring that not a single gap is left exposed to the corrosive elements. In the subassembly hall, massive jigs act as the mold for our future, holding 400-ton segments with absolute rigidity. The building is alive. It breathes, expands, and contracts, shifting its weight across flexible joints as the sun moves. The heavy lift sequence begins. A 50-ton module is prepped for its ascent to the 150-meter mark. Data is our most valuable resource. Every millimeter of movement is tracked, analyzed, and corrected from our central command. Diamond-encrusted blades make short work of reinforced concrete, refining the edges of our monumental foundation. The shift ends, but the structure waits. These silent giants are the result of millions of hours of human and robotic labor. The descent begins. 400 tons of nuclear-grade steel are lowered into the pit, where the margin for error disappears entirely. Magnetic sensors act as our eyes, tracking the sector's position to within a fraction of a millimeter in real time. Protocol is absolute. Every physical movement is verified by a two-man rule to ensure zero deviations from the assembly plan. High-pressure lubricants are injected into the load-bearing pivots, preparing the joints for the immense stresses of magnetic activation.
This 70-foot robotic arm is the centerpiece of the new production line, capable of assembling a vehicle chassis in under 3 minutes.
Plasma torches slice through 100-millimeter plates like paper, but with a surgical precision that defies their violent appearance. We use high-energy X-rays to look through the steel. A single microscopic bubble in a weld could lead to a catastrophic vacuum failure. On the ground, massive transporters with hundreds of synchronized wheels move the sectors with the grace of a living organism. Liquid nitrogen at -196 degrees Celsius pre-cools the superconducting paths, preparing the magnets for their zero-resistance state. The central solenoid, the strongest magnet in human history, is compressed by hydraulic force to resist its own internal pressure. We are creating a vacuum deeper than the space between planets. At 10 to the power of -9 Pascal, the vessel is ready. Beryllium coatings are applied in a controlled purple glow, creating a heat shield capable of facing the sun's raw power. Torque values are absolute. Every bolt in this structure is tightened to a specific Newton meter, logged and sealed. The facility's lungs' massive ventilation systems work overtime to maintain the ultra-pure air quality required for nuclear assembly. Finally, we enter the cryostat, a silver cathedral of technology that will soon be the coldest place in the known universe. The cryopump system is the facility's heart, maintaining the ultra-low temperatures required for superconductivity across miles of silver conduits. Thousands of fiber optic sensors are threaded into the structure, providing a real-time nervous system that monitors temperature to within 1/1000th of a degree. Radiation shielding is absolute. LED glass windows, 1/2 meter thick, provide the only visual portal into the reaction chamber. Traceability is key. Every single component, down to the smallest titanium bolt, is laser-etched and logged into our global database. Our digital twin platform mirrors the physical reactor, allowing us to simulate stress and heat loads before they even occur in reality. High-pressure cleaning sequences remove even the smallest speck of dust. In a vacuum this deep, a single hair could be a catastrophic contaminant. Blanket shield modules, made of rare beryllium, are stacked with precision. They are the frontline defense against the plasma's heat. The electrical backbone is connected. Gold-plated pins ensure zero-loss signal transmission for the reactor's complex control systems. We are looking at the neutral beam injector's massive particle accelerators designed to kickstart the fusion process. Helium leak tests are the final hurdle. If a single molecule of helium escapes, the entire assembly sequence is halted until the breach is found. Water management is on a city scale. Millions of liters must flow through the walls to keep the steel from warping under the star's heat. The magnetic cage is taking shape. We are designing a field so powerful it can suspend 100 million degree plasma in mid-air. Gigantic copper busbars are bolted into place, designed to carry the massive currents required to ignite the fusion reaction. The adjacent substation is the most powerful on the continent, drawing enough energy to jumpstart a star from the national grid. Inside the control room, the status boards are turning green. Every sector, every system, is now reporting ready for the next phase. Pressure testing is the moment of truth. We push the structural limits of every valve to ensure they can withstand the massive surges of an operational reactor. Inside the torus, the scale is overwhelming. Thousands of components must align perfectly before we can even think about igniting the plasma.
As we move deeper into the complex, the scale of the operation becomes apparent. The structural challenges here are immense, but the output is critical.
Surface finishing is handled by high-speed robotic polishers, removing even the slightest burr that could cause an arcing event inside the vacuum. 500 tons of hydraulic force are used to shape the prototype shield plates, testing the material's elasticity under extreme stress. Eddy current probes scan the surface for subsurface cracks. We are looking for flaws that are invisible to X-rays and the human eye. The primary airlocks are sealed. These massive steel teeth ensure that the vacuum environment remains isolated from the outside world. The gyrotrons are the reactor's heaters. They must be calibrated to fire microwave beams with perfect accuracy to heat the plasma to millions of degrees. The assembly hall is a 2-4-hour battlefield of light and steel, where multiple sectors are refined simultaneously to meet our strict deadlines. Liquid helium is our ultimate coolant. At 4 degrees above absolute zero, it transforms ordinary cables into powerful superconductors. Human strength is still required. Specialized torque multipliers allow our engineers to secure the massive baseplate bolts to exact specifications. The pumping sequence begins, drawing out trillions of air molecules until only a pristine, empty void remains inside the vessel. Titanium's strength-to-weight ratio makes it ideal for our cooling pipes, shaped by CNC precision to fit the reactor's tightest curves. From the cryo plant, we manage the most complex refrigeration cycle on Earth, pushing the boundaries of thermodynamics. The final gap check, 2 millimeters, exactly as planned. The precision of the chi to b n chi chi t is now officially verified. Diagnostic ports are the eyes of the machine, housing hundreds of sensors that will monitor the plasma's behavior from every conceivable angle. Gold-coated bolometers measure the raw heat radiation of the star, designed with microscopic precision to survive the most intense environment on Earth. The first wall tiles are the frontline armor, made of carbon composites to absorb the initial blast of energy during the fusion ignition. High-power lasers are used for Thomson scattering, measuring the plasma temperature by pulsing beams through the vacuum windows at light speed. The entire 23,000-ton machine sits on seismic isolators, protecting this delicate technical marvel from the slightest earth tremors. Endoscopic inspections are the final check, ensuring that every cooling channel is free of debris before the primary water circuits are sealed. Support structures for the magnetic coils are built to resist forces that would snap ordinary steel like a toothpick held by massive industrial bolts. From above, the cryostat lid reveals the sheer complexity of the project, a chaotic but perfectly engineered forest of feeders and pipes. Thermal isolation is absolute. Any heat leak at these temperatures would cause a catastrophic quench of the superconducting magnets. Hydraulic torque wrenches ensure uniform pressure across the flanges, creating a seal that can withstand the extreme vacuum of space. The baking process begins, heating the vessel to 200 degrees Celsius to boil off any remaining water molecules or impurities. High-speed cameras, capable of thousands of frames per second, are shielded in lead to capture the plasma's turbulence without being destroyed. The feeder tunnels are the machine's arteries, carrying the massive current and liquid helium required to power the superconducting coils. Every seal is a barrier against disaster. We use specialized vacuum greases to ensure the integrity of the primary containment system. As night falls in the assembly hall, the sheer scale of our ambition is reflected in the shadows of these steel giants. This is the moment of peak tension. The ninth and final sector is lowered into the pit, closing the circle on years of manufacturing. Alignment is no longer a calculation, it is a physical reality. We are merging 9 massive components into a single, seamless machine. Inside the pit, specialized robots take over. These compact welders are designed to operate in spaces too narrow for any human to enter. Tungsten electrodes deliver a precise arc, fusing the nuclear-grade steel at temperatures that would vaporize ordinary materials.
Behind me is the central part of the diverter joint, where the superheated plasma will be extracted.
Every millimeter of the field weld is scanned using ultrasonic arrays, searching for flaws in the molecular structure of the joint. Hydraulic tensioners apply hundreds of tons of force to the flanges, pre-stressing the vessel to withstand the magnetic loads to come. Thermal expansion joints are calibrated. The machine must be allowed to grow by several centimeters as it heats up during operation. We are navigating the canyons of the machine, where the vacuum vessel meets the massive poloidal field coils in a dance of tight tolerances. Electrical feed-throughs are the bridge to the outside world, designed to maintain a perfect vacuum seal while carrying gigawatts of power. Even with robots, human expertise is the final anchor. Our engineers secure the critical baseplate bolts with carbon fiber precision tools. The cooling manifold is a masterpiece of fluid dynamics, splitting a massive torrent of water into hundreds of individual channels. High-pressure helium is piped in for the final leak detection cycle, ensuring the integrity of the primary containment boundary. The SSAT jigs, the steel giants that held our sectors for years, are now being disassembled. Their mission is a success. Look at the result, a perfect silver torus. The vacuum vessel is now a single, unified pressure boundary, ready for the fire to come. The machine is complete. 23,000 tons of the most advanced engineering in history now standing ready within the cryostat. We are no longer counting in years, but in seconds. The countdown to the first plasma is the heartbeat of a new era. Power flows. The massive switchgears engage, sending gigawatts of energy into the superconducting heart of the machine. Superconductivity is achieved. At minus 269 degrees, the magnets are ready to weave their invisible cage.
The integration of these systems represents a significant leap forward, allowing our team here in the control room to oversee every critical juncture of the process.
Initiation begins. This is the moment where theory becomes the ultimate physical reality for the entire human race. The magnetic field is a masterpiece of stability, holding the 100 million degree fire in a perfect, untouchable embrace. The structure holds firm. Every bolt, every weld, and every sensor is reporting perfect structural harmony under the load. This facility is a testament to what humanity can achieve when we focus our collective intelligence on a single, impossible goal. Every detail mattered. From the largest sector to the smallest drop of coolant, precision has been our only religion. This is the victory of the engineers, the men and women who dared to build what many said was impossible. We are looking at a future of limitless clean energy, a world where the stars are no longer out of reach, but under our control. The vacuum vessel is sealed. The mission of construction is over. The mission of energy has just begun. As the sun sets over ITER, a new sun is preparing to rise within. Thank you for joining me in this journey through the edge of engineering.